Hello everyone, welcome to Dakshana e-classroom program. So up to last lecture we talked about fluid, basically or one part of fluid where fluid was at rest, and then we tried to understand the behavior of fluid, some terms related to it, some properties of fluid like density, is it variation of density, pressure, what is exactly pressure and how fluid apply pressure, and different like properties where like fluid behave in case of application of pressure, like it apply at one, like always doesn't matter what is the orientation of surface, the fluid apply pressure to any surface normal to it, right? So similarly we saw many like properties, and then we saw some principle like Pascal's law, Archimedes principle, law of floating. So in Archimedes principle we understood that how some bodies can float, and when they float, the physics behind it, why like some bodies are able to float, some bodies are not able to float. So this is like in every situation. And we also discussed one more case, that like pressure in accelerated fluid. In that case also, if we look at the fluid, then ideally it is at rest, the container was actually accelerating. So means overall, if I tell you, then the part that we have discussed, it's basically understanding fluid when it is at rest. Clear? And I told you in the beginning that science, that physics, the part of the physics we call that study of physics, like fluid at rest we call hydrostatics. Next comes, let's say if fluid is flowing, fluid is moving, fluid is it having some velocity, or like moving through a pipe or any like tube cross section, then how things changes for that? Does it behavior still remain same? Next things comes, does it carry some energy? What will be its velocity at some point? What will be its pressure? Different parameter, energy, what type of energy, how it carry, and velocities, and how with the help of fluid in flow we can understand many things, many like some of the experimental results, some observations, like you might have seen in football and even in cricket also, ball swing, is it? So like when cricket ball it's like rotating, then it can even change, it can turn in the air. How is that possible? Is it many time like when like wind blow at very high speed, sometimes like lose, is it like rooftops, they like simply leave off, is it, or flow off? How, why that happen actually? Even when like doors of that room is closed, still it happened that it's like comes out. So and like these are some practical things. And aeroplane, right, you know, it's flying in the sky, then why and how, like aeroplane, why it doesn't fall, who support that? Because it's like quite heavy, then how that weight of aeroplane is still supported in the air? So we can understand, you can like understand the physics behind all these things by understanding the next part of this fluid. You can say fluid dynamics or hydrodynamics, is it? So here we are going to talk about same fluid but from different angle. When fluid is in motion, fluid is flowing. Okay, so fluid we have already understood what is fluid. And a substance which can flow, substance which cannot bear any amount of shear stress, that we can define a fluid. Okay, so now the fluid, we will be talking about the part of fluid where fluid is in motion. Okay, so let me tell you, let me define few terms related to it that will be required. First comes like incompressible fluid, then comes your non-viscous ideal fluid, steady flow, uniform flow, non-uniform flow, streamline, and laminar turbulent. So these are few terms which we require actually, or we will be dealing like a fluid is flowing, steady flow, and ideal fluid. So what does mean all those things? So let me tell you all about them. So first comes is, let's say, incompressible fluid. Okay, so these are different terms. Incompressible fluid, you can understand it simple, even clear from its name. Okay, so incompressible fluid means a fluid, is it, which cannot be compressed, or you can say the density of fluid is constant, and we can define it in for incompressible fluid, compressibility will be equal to what? Compressibility, that is equal to 1 by k. B is bulk modulus, so here compressibility k become like 0 and B become infinity, almost tending to infinity. So very high bulk modulus, it means like almost change in volume. For applying change in like some small change in volume, you need to apply infinite amount of force. So this fluid which is having this property, means which cannot be compressed, we will define that incompressible fluid. Next comes non-viscous fluid. About this, basically there is called viscosity. It's one property of fluid. We discussed that in separately. There is one chapter like simultaneously. I'm like almost like with this. Just next there are like sometime even before. So that is elasticity and viscosity. So in that chapter we talk about viscosity property of fluid in detail. Okay, so what is exactly viscous or viscosity property? Here what happen, if a fluid is flowing in layer, then just like solid case is there, let's say two bodies in contact and there is relative motion. If the surface is rough, then one body opposes the relative motion of other body by the force we call friction. The property is because of roughness of this contacting surface. Exactly in same manner in liquid also, because of intermolecular forces between liquid atoms or molecules, we call that cohesive force. So molecule of one layer get attached or bonded to the other layer, means the molecule which is having lower speed will get attached to the higher molecule which is having higher speed, so they will try to like oppose, is it? So exactly in viscosity also, when fluid flow, the lower layer which is basically at low speed opposes the relative motion of upper layer, is it? So this also sort of act like friction in fluid and we call that viscosity. So non-viscous fluid, we can say when the viscosity of a fluid is 0, means there is no opposition offered by the layer of fluid, is it? We can call, so non-viscous liquid, the viscosity of liquid is or liquid here I mean you can say fluid is 0 is called as non-viscous liquid. So we measure that basically coefficient viscosity coefficient in terms of eta. This is called coefficient of viscosity, and eta equal to 0 for non-viscous liquid. Okay, so here we can say, means there is no resistance offered by different layers of fluid, is it? No, when even relative motion also there. So that is the meaning of non-viscous fluid. Another comes ideal fluid. So if I tell you that does there exist any fluid like which is having viscosity 0 or which is perfectly incompressible, the answer is no, there doesn't exist any fluid which is perfectly like you can say incompressible or perfectly non-viscous. So practically means in real terms, no fluid is actually non-viscous ideally or incompressible. But to make the things easy, to make this study easy, to understand the fluid, understand the physics for fluid, we define few terms and we study according to that, so that we can focus, we can like understand some part of fluid easily. So for that we are going to define a fluid that is ideal. It's just definition. Practically no fluid is ideal, but when we will be studying in this part, we will by default, if it is mentioned, is it, until unless it's not specially mentioned that it's like not ideal fluid, otherwise most of the time like it's already or always it's ideal fluid. So this is a concept which help us in understanding the things, the topic, the concept easily, right? Because if we directly jump in understanding real fluid, it will be very difficult. So that's why we will go step by step. So ideal fluid, basically a fluid which is non-compressible and non-viscous. Is called ideal fluid, right? So ideal fluid means fluid which is non-compressible and non-viscous is termed as ideal fluid. In reality, there is no ideal fluid. It's just a concept, right? So practically if we look at it, then there doesn't exist any ideal fluid. Okay, so this is about, so by default, like most of the time I'm telling you, when we will be studying this part, we are mostly going to talk about ideal fluid until and unless it's especially mentioned in the problem that we are talking about real fluid. Okay, so by default you can say the fluid that we will be talking about will be ideal. Okay, so now let's say the fluid is flowing through the pipe, is it? So then comes like when it comes steady flow, is it? What is the meaning of that? Steady flow. So I mean, like, let's consider there is a pipe, is it? Non-uniform cross section. Fluid is flowing through this pipe like this. Now what happened? Different possibilities can be there. One is fluid velocity at this point, fluid velocity at this point, fluid velocity at this point, fluid velocity at this point. At every point fluid velocity is constant, means with position, and also with time it's not changing, is it? So what is like, I mean, like another condition maybe at every point velocity is different, with time it's not changing. Another possibility can be every point velocity is different and it's changing with time also. So like different combinations, different possibilities can be there, is it? So for that we like define, okay, if this is the condition we will call that steady flow, if that is the condition we will call something else and something else, so on. So what is a steady flow? Just understand it, look at it. Let's say the velocity here v1, velocity here v2, velocity of fluid flow, velocity of fluid flow here v3, and velocity of fluid flow here v4, is it? So in case of steady flow, if the velocity of fluid flow is not changing with time at any point, but it can be a function of position. Means if I just focus on this point, then the velocity of fluid flow at this point should not change or must not change with time. If right now its velocity at this point is v1, After 1 minute, after 1 second, like 1 hour, 30 minutes, 20 minutes, the velocity must remain same. That will be the steady flow. But it can change at different point. If I am changing the point, yes, the velocity at this point can be different. Velocity of this point, and similarly velocity at this point can be different from this. Velocity of this point can be different from this. But at any point, the velocity must not be a function of time. It can be function of position, means at different positions the velocity can be different, but any point, at any position, velocity must not change with time. This type of flow is termed as steady flow. Okay, so there are like a few more terms. Let me like define those. Let me write those. Okay, next is uniform flow. So what is uniform flow? If velocity of fluid flow at every point is constant, and that too it's not changing with time, then that flow will be termed as uniform flow. So this normally happen when the cross section of the pipe is constant. In that situation, this velocity, this will be equal, and that will be constant with time also. That is called as uniform flow. So non-uniform, it's just like opposite of that. Velocity at every point, it's not constant. At any point it's different, and it's changing with time also. So if speed or velocity, it means exactly same here actually, like this magnitude, and we are talking about the direction also, then it will be velocity. So if speed of fluid flow is not constant at this point, speed at, let's say this time is v1, after some time it's changing v1 prime, v1 double prime, so on at all point, and another point at this point also, means v1 is not equal to v2. So speed of fluid flow is not constant at all point, and also with time it is simply termed as non-uniform fluid flow. Next comes streamline flow. So first thing is, what is streamline? Streamline is actually defined as the path of particle of fluid when it is flowing. A particle is flowing, like fluid is flowing. So if you just trace the path, each path, like path of each particle, the path of the particle will be termed as streamline. And it can be curved, it can be straight line, depending on the like cross section and many other factors. And tangent to this curve or tangent to this streamline will give you simply velocity of fluid flow. Another thing comes is like this two streamlines does not cross, does not intersect, and at any point if the density of streamline is higher, it's like crowded, more crowded, that means at that point the velocity of fluid flow will be higher. And if each element of liquid passing through, let's say this point, is following exactly same path as the preceding particle with the same velocity at every point, the fluid flow will be termed as streamline flow. Let me tell you, streamline is, it may be defined as the path of the particle, maybe straight line or curve depending on, is it, and tangent to which at any point give the direction of the fluid flow. And if each element of liquid passing through a point, let me say element passing through this point, so this element is passing through next time from here, then the next element passing through this point must also pass through same point with same velocity. Let's say here velocity is v, so particle 1 which passes through point A is passing through this point, okay, let me write it d with velocity v. Then next particle which is passing through point A must also pass through D point with same velocity. That flow will be termed as streamline flow. And two streamline cannot cross at any point, and greater is the crowding streamline, higher will be the velocity of fluid particle at that point. So this is the meaning of streamline flow. And next comes laminar and turbulent. Let me define those also. Okay, next is laminar flow. So laminar flow, basically here It's also steady flow, or synonymously we call it's like also streamline flow. Streamline flow we understood, but here things becomes little bit different. Is the flow is over a horizontal surface and fluid flow in the form of layers actually. So flow will be over horizontal surface and fluid will flow in the form of layers. This is like layers. The velocities may be different actually. So this type of flow is termed as laminar flow, and steady flow and move in the, so in a liquid, if a liquid flowing over a horizontal surface with steady flow and move in the form of layers of different velocities which do not mix each other, these like layers do not mix each other, this is termed as laminar flow. Normally basically like these categorization are based on fluid velocity. If fluid velocity is relatively low, then the behavior nature of fluid flow is laminar or streamline actually. It will be like proper regular mannered, and each particle will be like having proper constant velocity, and streamline will be also there like different. So normally streamline or laminar flow means like velocity of the fluid flow is quite low, then it will be the nature of the flow will be laminar, and we call that like laminar flow. Similarly, when the velocity of fluid flow become quite large, is it? Now next question comes like how much large. So for that we have also defined one criteria, I mean like that was defined by Reynolds, and we call like there is one critical velocity. I will define after this also. So you can say when the velocity of fluid flow is below the critical velocity, then flow will be laminar. If velocity of fluid flow become more than critical velocity, your flow turns out to be turbulent. So you can say velocity is less than critical velocity. Of fluid flow, then it is laminar flow. When velocity of fluid flow become quite large or more than critical velocity, it turns towards turbulent flow. In turbulent flow basically it's random flow actually, where the velocity, speed and direction of fluid velocity, of particle velocity keep on changing regularly and randomly, is it? And this normally happen when the velocity become quite large. So when fluid flow at higher speed, so that motion of particle become disordered or irregular, the flow is termed as turbulent flow. In turbulent flow, the path and velocity of particle keep on changing regularly and randomly, point to point and time to time. That flow means like it's just, you can say completely, if a flow is in proper manner, proper like order, that is your laminar or streamline flow. When speed of fluid flow is quite large, there will be mixing of fluid, no proper velocity is there, velocity of particle is changing, direction is changing, is it, path is just changing regularly and randomly, we will call that a turbulent flow. So in turbulent flow, like let's say initially it started and then some disturbance comes, or even like sometimes speed is higher, then it keep on mixing, and this part like these condition will be also there, velocity and path of the particle will keep on changing randomly, so we will call that a turbulent flow. So next comes like all this categorization is based on the speed of fluid flow, and there also like means if we are having let's say wide large open surface plate, then one condition, another we are having pipe of some cross section, another we are having pipe of different like higher radius. So does like condition for velocity for both the cases is still same? So there is like some other parameter also, and for that we define one Reynolds number also. So Reynolds number also keep one character condition, is it, about a fluid flow, when it will become laminar, when it will be turbulent, something like that. So let me define those terms and let me tell you those condition, critical velocity and Reynolds number. So what is exactly Reynolds number? Let me tell you. So critical velocity also let me define first, then we will like say that based on if velocity of fluid flow is less than critical, it will be laminar, more than critical, it will be turbulent flow. Okay. Okay, next is Reynolds number. So basically it is a purely a dimensionless number, and it is defined as the ratio of inertial force per unit area to viscous force per unit area. So sort of like you can say it's defined for real fluid, actually not for ideal fluid, you can say. And Re can be inertial force per unit area divided by viscous force per unit area. If I consider a tube of diameter, let's say d, and fluid velocity v, eta is its viscosity and rho is the density. So this is viscosity of fluid and rho is the density. And another thing, actually, in case of Reynolds number, so this is one when fluid consider fluid flow through a pipe, right? So here fluid is flowing through the pipe. Maybe another condition, fluid is flowing through a rectangular cross-section pipe. Different possibilities are there for them. For this this basic definition remains same, but the formula changes little bit. We don't need that, we simply need it only for the pipe. So I'm going to write the formula only for the pipe. And another point here which I want to mention is that the Reynolds number value, is it for flow, changes from system to system. Another thing which I observe is like in even different books the value is mentioned different. For you people, you follow the values mentioned in your NCERT textbook, is it? So I will be writing based on that and you also cross check it. So the point is, in different book, if you just go for the number of Reynolds value of Reynolds number, you will find a difference. So that's why, because NCERT and like CBSE and all those exam conducted, they follow the CBSE books or NCERT books. So the values given in NCERT book, you follow that. Okay. So let me tell. So let's consider fluid flow through a pipe. So diameter of the pipe is d and velocity is v, eta is the viscosity and rho is the density. Then for this, if I write Reynolds number, it comes out to be rho v d by eta. This is the Reynolds number, and Reynolds number basically helps us in determining the type of fluid flow. It determines the fluid flow type, means whether flow will be like laminar, turbulent and transient. So here right now I am talking only for pipe. So according to NCERT convention, if Re is less than 1000 for a pipe, it's laminar flow. Re less than 2000, greater than 1000, and Re greater than 2000, this is turbulent flow. And here it changes from laminar, in this range changes from laminar to turbulent. This is called transient flow. Where fluid flow changes from laminar to turbulent. So for a pipe only, if you change the system, change the dimension, like even maybe square cross section pipe, things will be different from that. Maybe fluid is flowing over some plate, is it? So large open surface area, for that Reynolds number will be different. So that's why like I am defining it only for pipe. This is the range of like value of Reynolds number for which fluid will be laminar, turbulent and transient flow, changing from laminar to turbulent. And this is the definition. It's a purely number. It is a dimensionless number. So it's simple, a pure number. Next comes here a critical velocity. Is it? So critical velocity, let me define here. Or critical speed of fluid flow. It is the maximum velocity, or you can write speed also, up to which the flow is laminar is called so how I can define for different systems. I will be knowing the Reynolds number for which the flow will be laminar, and we know Re is equal to rho V d by eta. So for I know the value of Reynolds number corresponding to maximum value of Reynolds number, is it? So let's say Re maximum value of Reynolds number corresponding to laminar flow, right? Then by this I can write V critical will be equal to Re eta divided by rho into d. So this will be the corresponding critical value of velocity for which the flow will be laminar. Substitute this value, this value, this value, you will be getting the corresponding velocity or critical velocity. So velocity less than this, flow will be laminar. Velocity, like you can say above, it will be tending towards turbulent flow. And exactly like if you substitute this value, then you can say beyond that value it will be turbulent flow. So these are different terms related to fluid flow, and like when we give like turbulent, laminar, etc., streamline, you must understand these meanings. These are also important. Now let's talk about, so let's say now we have fluid which is flowing through a pipe, and how we can relate different terms, different things: velocity, pressure, speed, kinetic energy, potential energy, and so on. So like these can be also, I mean, like just imagine that if fluid is flowing through a pipe, then you want to know more about the fluid. Is it its behavior? It's like, so what can be like, what is its velocity at different point? How can we know it? What is the relation between them? If fluid is flowing through in a pipe, going up, going down, what will be like velocity? How much pressure we need to apply to move send the fluid from like bottom to some height? So different relations. So for that already like scientists have derived different things. We just need to understand, we just need to learn those concepts and formulas. Let's talk about that. So first comes our equation of continuity. Let me first erase this part. Okay, so next is equation of continuity basically. So it gives us the relation between velocity and area of cross section. What exactly it is? Let's consider this is a pipe of maybe some variable cross section, and fluid is entering here with some velocity v1 and it's exiting out here with velocity v2. Area of cross section is a1 here, area of cross section at this point is a2, and if density, let's say here rho1, it's rho2, then in this situation we are assuming that no accumulation of fluid is, and no source of fluid is also there, no accumulation and no supply of fluid in between the pipe, right? I'm like, it's not, there is no something, some tank, storage tank where some fluid is going inside it, or no even like pump or something which is supplying it. In that situation, it here simply fluid is flowing through a pipe, right? In that situation, what will be the relation between these quantities? That we can write with the help of equation of continuity. So it is basically, it is based on conservation of mass, conservation of mass. And what is that actually? The rate of mass entering at, let's say, and let me write 1 must be equal to rate of mass of fluid exiting at and 2. So this is and 2. This is equation of from here we. So what is like let's say area is A, and if I say in delta t time it has traveled up to here, like let's say this, so this will be like how much distance, v1 into delta t, is it? And exactly in same time fluid from here will be traveling up to here, so this will be your v2 into delta t. So this much fluid in this much will come out, and this much amount of fluid might be entering in same time because it's completely filled, so no further accumulation and supply of fluid can take place. So whatever the fluid entering in delta t time at this end must be coming out exactly at that end, is it? So with this can write, let the mass, or I will say the mass of fluid entering at and 1 in delta t. So that can be written as, because area is a1 and because it's moving with velocity, I am assuming this is very small interval, so for this interval almost the velocity is still remaining constant. So then I will say its distance, how much traveled, v1 delta t. So volume will be equal to what, v1 delta t, length multiplied by area multiplied by density will be the mass. So that can be written as rho 1. This is v1 a1 into delta t. So this is rate of mass entering in delta t time. Similarly, mass of fluid exiting at and 2 in delta t time, that can be also expressed as rho 2 v2 a2 into delta t, and this implies rho 1 because conservation of mass flow. So this is rho 1 a1 v1 delta t must be equal to rho 2 v2 a2 delta t. Delta t cancelled out, and we are getting finally rho 1 a1 v1 is equal to rho 2 a2 v2. This is also that mass flow rate is also constant. And here, if fluid is incompressible, that like mostly we deal with this only incompressible fluid, in that situation rho 1 will be equal to rho 2, and this will implies a1 v1 equal to a2 v2, and this is also called volume flow rate. Flow rate of fluid is constant. So here we get actually the relation between area of cross section of the pipe and velocity of fluid at that point, and here area multiplied by velocity is remaining constant. So if in this situation here you can see the area is decreasing, then definitely to keep this a into v constant, velocity must increase, is it? So like area decreasing, so velocity must increase. So wherever let the pipe is having higher cross section, velocity will be low, and vice versa. If cross sectional area is small, velocity will be high. So we can even get the relation, just this is velocity versus area, it will be just like this. Higher here, like lower is the area, velocity will be higher. Higher is the area of cross section, velocity will be lower. So this is the relation, and simply this relation or this is called equation of continuity. Okay, see one simple problem. So here a pipe is there through which the fluid is entering. Here area of cross section is A, fluid entering with the velocity 10 meter per second, and here like it's dividing into two small cross section pipe, and velocity of fluid in this pipe is given to you, and there you are asked to find. So here with the help of equation of continuity we can easily solve it. So by equation of continuity, what we can write at this point, like rate of fluid flow entering, is it is entering will be equal to rate of fluid exiting at both the ends. So this implies here I can write A1 V1 is equal to A2 V2 plus A3 V3, because here like this pipe is itself dividing into two parts, so it will be exiting from exiting, and even if the pipe is like bended like this, we will be like checking at which point it is entering and at which point it is exiting out. So one pipe is, let's say, like this shape, and here in this situation, let's say, so it's exiting and exiting, then we will write entering here. So this A1 V1 will be equal to A2 V2 plus A3 V3, means wherever, like whatever the number of points it may be exiting out, like say it is exiting here also, then it will be A1 V1 is equal to A2 V2 plus A3 V3 plus A4 V4, something like that. So exactly by this way we can write it in this manner, and this area is A, velocity is how much, 10 meter per second, area, let's say this is A2, so it's A by 3 multiplied by velocity is 15 plus this is A by 2 multiplied by velocity V. Clear? So this comes out to be A gets cancelled out, this is 10 equal to 15 by 3, that is 5 divided by V by 2, so 5, and this implies V is coming out to be simply 10 meter per second. So that's simple application of equation of continuity. Next comes like, okay, this is about simple pipe. If pipe area of cross section is changing, area and velocity, how they are related, we understood that with the help of equation of continuity. Next comes maybe like fluid is entering up to some height, maybe coming down, so there we need some like energy relation and some pressure relation also, and for that we have already one like concept that is called Bernoullis Principle, and it's a very important concept. So let me tell you what is exactly Bernoullis Principle. Okay, next is Bernoullis Theorem. It basically relates the energy of fluid. So let me define, first let's consider here a pipe. We are having a pipe. The cross section here I am considering a non-uniform cross section, and let's say the area of cross section at this point is A1 and at this point it's A2. The velocity of fluid flow and this will be a V2 and this it's V1, right? And to define, because we need kinetic energy, potential energy and work done by pressure force, we call that pressure energy also. So to define the energy, potential energy, we need one reference line actually. This reference line I am taking here, you can take it reference line here, reference line here, reference line here, or reference line can be even taken at the center of one of the part. You can take a here also, it's up to it's your choice, nothing wrong in anything. Wherever, whichever the point you find it comfortable, you find it easy, you can take that as your reference line. So this is the reference line I am taking for calculating potential energy. So let's say this is the, and from this point I consider its height is, let's say, h1, and height of this point, let's say it's h2. Okay, then it comes, next thing is we need to define here kinetic energy and potential energy. The fluid is continuously flowing. It's not like we can't take any particle of the fluid, then how we can still define the kinetic energy and potential energy? Let's see, I am telling you the approach. So what is the approach actually? Here we consider one very small interval of time. So let's consider very small interval of time. Let consider a small time interval delta t. Then what will happen? The fluid is entering here in delta t time interval. It will be like, let's say, traveling this much distance. This can be written as, distance can be written as v into delta t. Then this fluid element, is it like fluid inside this region, I can take this is my element and its mass is m. And kinetic energy, because for this interval, very small interval of time, like very small length of the pipe, I can take almost the velocity of fluid is also constant. Then I can take its mass as m, and kinetic energy I will write it's m into half into m into v square. So that way we can write the kinetic energy, and exactly I can take this fluid element and its mass, so I can write the potential energy for that element also. So exactly in this manner we write the element energy of fluid element, kinetic energy, potential energy and so on. So exactly here, and similarly in because here speed is higher, according to the area of cross section we can see it's smaller, so I can just relate little bit, so its speed will be higher. So the element fluid element will be traveling little bit higher distance in same interval of time in this region. So I will consider this is my another fluid element. Okay, then let's write the kinetic energy. Is it at end 1, this is end 1 and this is end 2. So kinetic energy of fluid element, kinetic energy of fluid element. So kinetic energy, I will write first thing is we need to write mass. Is it mass will be equal to what? M mass of element. So I am considering element, this much element, and that's length can be taken as V into delta T. So velocity is V1, so I will write V1 into delta T. So mass of the element here for time delta T. This can be written as mass density. I am considering here incompressible fluid, and one more important point about Bernoullis principle is that this Bernoullis principle is defined only for ideal fluid. This principle, if the fluid is not ideal, fluid is a real fluid, in that situation this doesn't valid properly. Actually it will not give you the proper result, and it is also defined for streamline and ideal flow. Is it? So I will write that condition, Bernoullis principle I will write later. So then mass of the element can be written as rho into density multiplied by volume. Volume will be A into V into delta T. This is the mass, is it? And if I write mass flow rate, then mass flow rate will be equal to what? dm by dt or delta T, that will be rho into A into V, and volume flow rate is given by flow rate, that can be written as, that is equal to mass divided by density will give you volume. So mass flow rate divided by density will give you volume flow rate, area into volume, velocity, that is your volume flow rate. Okay, so let me write now kinetic energy of element at end 1. So kinetic energy of fluid element at end 1, this can be written as, let's say K1, this is equal to half rho A1 V1 delta T, this is mass multiplied by V1 square, right? Similarly at end 2, kinetic energy K2 can be written as half rho A2 V2 delta T, this is mass multiplied by V2 square. This is kinetic energy at end 2. And similarly the potential energy of fluid element so let's say end 1, this I will write this U1, so mass into G into H, mass is rho A1 V1 delta T multiplied by G multiplied by H1, and at and 2 this will be U2 is rho V2 A2 delta T multiplied by G into H2. This is potential energy. And here one more thing, so pressure inside the fluid, or this velocity I am just writing here, pressure will be, I hope you must be agreeing that fluid, is it? Pressure must be pushing the fluid upward, then only it will be moving, otherwise it's not possible. So pressure at this point, if I take its P1, it must be directing in this direction. And just think about it, what will be the direction, in which direction the pressure will be acting on the fluid element? Is it this way or this way? The answer is pressure will be acting in this direction. Let me write it P2. You might be having like doubt, if anyone, let me clear, because pressure it can't like apply a tensile force. Pressure can't pull anything, it can only press, it can push actually. So and another thing you can see, if pressure is, let's say, acting here, then we don't need to apply pressure here because it will be automatically pulling it, is it? And that's not possible actually. So pressure always, like here, pressure will be acting in this direction, remember that. Then on this element I can write work done by pressure force. So pressure into area will be the force multiplied by the displacement will be the work done by pressure force. We call that pressure energy also. So work done by pressure force, or you can write pressure or pressure energy. So at and 1, this will be equal to, let's say, WP. That can be again pressure force is equal to pressure multiplied by area into displacement V1 into delta T. And at and 2, I will write WP2 will be equal to again pressure. And one more thing, pressure work done by pressure force here will be positive because pressure applied in this direction, displacement is also in this direction, it will be positive. And pressure is acting in this direction, displacement of fluid element is in right direction, so it will be negative. So I will write minus P2A2 into V2 into delta T. Clear? Now I can use conservation of energy principle. Just remember these results. Okay, write down. This is potential energy and kinetic energy. Then because there is no dissipative force, already I am considering it's ideal fluid, means no dissipating force, nothing is present here. So work in principle of conservation of energy theorem can be applied here. So you can write as fluid is ideal, means incompressible and non-viscous and streamline flow. So in this situation, no dissipating force, right? That's why we can apply by conservation of energy principle. So we can write delta K delta U equal to work done by external agent, right? So here external, here basically pressure force. So this can be written as final minus initial half rho A2 V2 delta T into V2 square minus half rho A1 V1 delta T into V1 square plus potential energy U2 minus U1. So it's rho A2 V2 delta T G H2 minus rho A1 V1 delta T G H1. This is delta K delta U is equal to work done. So work done is positive, total net work done, that is positive, minus, so P1 A1 V1 delta T minus P2 A2 V2 delta T. And let me rearrange it now. Delta T delta T can be cancelled from everywhere. Okay, and by continuity equation, another equation of continuity, what I can write, A1 V1 will be equal to A2 V2, right? This quantity, that is volume flow rate V dot. Let me write it Q dot. Okay, so this implies A2 V2, A1 V1, A2 V2, A1 V1, A1 V1, A2 V2. That is also gone. What I am left here, rho V2 square, half rho V1 square, rho GH2, rho GH1 and so on. So let me write that part here. We are left with half rho V1 V2 square minus half rho V1 square rho GH2 minus rho GH1 is equal to P1 minus P2. Right? This is here P1 minus P2. Let me rearrange all like one term or terms related to N1 and N2 on one side and another side. So this is P1 plus half rho V1 square plus rho GH1 equal to P2 plus half rho V2 square plus rho GH2. So this is pressure energy per unit mass per unit volume. Here we can divide it by rho G. This is P1 by this is rho G plus V1 square by 2G plus this is H1 equal to, I can write P2 by rho G plus V2 square by 2G plus H2. This is called pressure head. This is called kinetic head. And this term is called potential head. So the Bernoullis principle is, and this is your corresponding to pressure energy per unit mass per unit volume. So Bernoullis principle says the sum of potential energy kinetic energy and pressure energy per unit mass or per unit volume of fluid remains constant. And by that I can write this is P plus half rho V square plus rho GH is equal to constant, or you can write P by rho G plus V square by 2G plus H is equal to constant. This relation is called Bernoullis principle, Bernoullis theorem. It's very important. Another point, remember, it should be fluid should be ideal fluid and streamline flow. For that purpose, for that condition, you will be able to apply this Bernoullis principle. If it comes like a real fluid, in that situation it will not work. Another point, even in case of streamline flow, you cannot apply like Bernoullis principle at two different streamlines, is it? So this is, I hope you are clear with how we write kinetic energy, how we write potential energy, and how we write pressure energy or work done by pressure, and then with the help of conservation of energy, how we related all of these quantities. So it give us a lot of like application. It give like with the help of this we can comment a lot of things out actually, right? And another thing is it's valid for ideal, remember that. And you cannot apply Bernoullis theorem for real fluid and between two streamline. Means this is like one streamline going like this, so in that we are able to apply, is it? At some point like one streamline at another streamline, it's then it will not be applicable. So remember that case. And this is all about, let's see some of its application. One simple application, let me tell you like one example. So we have here a pipe of variable cross section, is it? Let's say here, so cross section area A1 and here cross section area A2. If velocity here is V1, then velocity here will be V2. And which will be higher? I think you are already positioned to answer that. I just want to know, like, and let's suppose it's placed at same horizontal level, so there is no kinetic like potential head. Then pressure at this point is P1, pressure at that point is P2. What do you think? Just imagine, just think about it, like at which point pressure will be higher? Is it at which point pressure will be higher? This is the question. We can answer it very easily with the help of Bernoullis principle. Let's see. So I will apply at this point. It's P1 half rho V1 square plus rho G H. H, I am just writing it. Next is P2 half rho V2 square plus rho G H2. Actually H both are same, so that's why I am simply cancelling out. I am left with this term. Let me rearrange this side. So it's basically P1 minus P2 is equal to half rho. This is V2 square minus V1 square. What do you think? Which one is higher? Definitely V2 is higher. By continuity equation, equation of continuity, we can write A1 V1 is equal to A2 V2. This implies as A1 is greater than A2, this implies V1 is less than V2. So this implies V2 is higher, means this quantity will be a positive, means this will be a positive, greater than 0, that implies P1 is greater than P2. This is also very important result. What it is saying? So in a pressure fluid flow, if at one point the velocity is higher, is it, then pressure will be lower. So when velocity is high, pressure will be low. At that point, pressure will be low. This is also the principle used in aeroplane. How? Let me tell you all those things. So with the help of this Bernoullis principle, we can understand a lot of things. We can see a lot of application of Bernoullis principle. Let me tell you one by one. Just remember the relation, just remember this equation. It's very important, don't forget it, just mug it up. Is it? P plus half rho V square plus rho GH is equal to constant pressure head, kinetic head, and this like head means you need to divide it by, when it is asking about head, you need to divide it by like rho G. So it will be H V square by 2G P by rho G. That will be your pressure head. This is energy per unit mass per unit volume answer. So this is all about Bernoullis principle. Let's next talk about their application or application of Bernoullis principle.